Welcome to the course Business Analytics and Data Mining Modeling using R part 2. So, in previous few lectures we have started our discussion on cluster analysis, and specifically we were discussing the distance matrix for categorical data. So, let us continue our discussion. So, we talked about two specific coefficients, matching coefficient and Jacob's coefficient, and how they can be used to measure categorical variables. Then we also talked about the situation, the scenario where both numerical variables and categorical variables are present. So, in such a scenario how we can what are the metrics which could be used to measure distance. So, Gaubert's similarity metric is one that could be used. So, let us understand this particular metric. So, to compute this metric, first all the variables should be scaled to 0, 1, and the reason for this is also quite obvious because we are also having categorical data in our data set. So, there the categorical data, it could be ordinal, it could be nominal, and typically we use dummy variables to to code these categorical variables. So, therefore, those dummy variables typically they are coded using zeros and ones, and therefore, the range is going to be 0 and 1. So, for that reason we typically scale our numerical variables also to this scale 0 1 scale. So, that is why the first line is asking for that explicitly. For example, first all the variables should be scaled to 0 1. The second step would involve taking weighted average of distances computed using following formula. So, this formula actually in a sense accommodates both the numerical and categorical variables. So, we look at this so Sij. So, in here we S by S we mean S indicates or denotes the similarity between two observations I and j. So, here you can see in the numerator part we have summation over 1 to p. So, that is because we have p number of variables. Then we have a weight value that is Wij so, where m starts from 1 to p. So, this is for each variable. So, for each variable we got to have these weights, and then similarity value for this observation. This is again for each variable Ijm. So, Ij stands for the observations I and j which are under consideration, and for each variable which would be changing from 1 to p. So, the product of the weight value and the similarity value, that is going to be used in the numerator part. So, we will take summation of all such values, weight and product of weight and similarity value, and in the denominator we are using the summation of weight values, right. So, let us understand how these values are going to be computed. So, first of all let us understand the Wijm, the weight part. So, Wijm is going to be 1 or specified weight. So, if we are going for equal weightage scenario where we are assigning equal weightage to all the variables, then of course the typical value is going to be 1. Otherwise, if we have different weightage for different variables, then that specified weight value can actually be used. So, typically the Wijm value is going to be 1 or a specified weight if comparison of measurements is valid, otherwise 0. So, if the measurements that is specifically we are talking about the similarity value, if that similarity value can be compared for both the observation I and j, then we are going to use this one 1, otherwise 0. So, let us move to the next category. So, if we have if our variable is binary categorical variable. So, Sijm, this is going to be 1 for indicating presence of attribute for both the observations, else 0. So, as we know that in categorical variable this particular discussion is quite similar to Jacob's coefficient. So, 1 indicating the presence of that attribute for both the observation and 0 indicating the absence of that attribute for both the observation. So, if the attribute is present for both the observation, then we will take SIJM value as 1. If it is not present, then we will take it as 0, just like in the Jacob's coefficient. So, there if there also in the Jacob's coefficient, if some of the variables were absent, some of the attributes were absent for both the observations, we did not we did not accounted that as a similarity thing. Similarly, here also SIJM is going to be 1 if the that attribute is present for both the observations. Let us move forward. So, if we talk about the non-binary categorical variables, so in that cases, so where we have the categorical variable having more than 2 categories, so where we are not using this dummy kind of coding indicating presence or absence. So, those kind of variables can also be covered here. So, for non-binary categorical variable, SIJM value is going to be 1 for match. So, that means 2 observation, for example, here we are talking about observation I and j, and for a particular variable if there are 3 categories, and for the for different observation if they are if they have the value the same attribute for same category for that particular variable. For example, if we take the status of a particular customer, whether the customer is employed or a student or retired, if 2 observations are having the same status, that is both the observation are having the employed values for the status variable, then in that case match is there. Therefore, the value SIJM is 1. Otherwise, if the match is not there, then the value is going to be 0. So, the discussion that we had in the previous lecture, that if the particular for a particular variable the attributes or the values, the categories are matching, then that in a way indicates the similarity. If it is not matching, then it indicates the dissimilarity. So, because it indicates the similarity, if the values match, the attribute value match, then we are therefore we are taking this value SIJM value as 1, otherwise 0. So, these 2 points that we just discussed, they will cover all the categorical variables. For numerical variables, we could use this formula to compute SIJM values. So, this formula, as you can see, 1 minus, then we have this value in the numerator XIM minus XJM divided by max of XM minus min of XM. So, this particular formula can actually be used. So, you can see the Gauber's similarity metric and specifically for numerical variables, the formula that we are using is quite similar to, we are using absolute differences here. So, those absolute differences are being used to compute this value, and then for categorical variables and numerical variables, once all these similarities value SIJM values have been computed, we can plug all these values here in this formula, Sij formula, and we can compute the similarity value for those 2 observations. About weight we have already talked about. So, in this fashion this particular similarity metric, Gauber's similarity metric, can be used when both kind of variables, continuous variables and categorical variables are present in the data set. So, with this till now what we have been able to cover is the distance between 2 observations. So, one important aspect of cluster analysis is computing distance between 2 clusters. So, now we are going to start our discussion on this particular aspect. So, how do we define a cluster? So, this is quite straightforward. A cluster is a set of 1 or more observations, right. So, the cluster can have even a single observation, as we have been discussing in previous lectures as well. So, the cluster is defined to have the cluster can be defined as a set of one or more observations. Now, distance matrix that could be used to compute the distance between two clusters. So, some of them are mentioned here. For example, minimum distance matrix, this is also called single linkage matrix. Then we have maximum distance matrix, also called complete linkage. Then we have average distance matrix, also called average linkage. Then we have centroid distance. So, let us discuss these metrics one by one. So, let us consider two cluster. First one, cluster A having m observations, A1, A2, A3 up to Am, and then the second cluster is cluster B having n observation, having observations B1, B2, B3 up to Bn. And the distance between these two clusters, cluster A and cluster B, can be defined as capital D A B. So, this is the distance between two clusters. So, we are going to use these notations for our coming discussion. So, let us discuss this first metric, minimum distance metric, single linkage. So, how this can be defined? So, distance between the pair of observations which are closest. So, these two clusters, cluster A and B. So, we consider all the observations between these clusters and identify the pair of observation, one observation belonging to cluster A and the other observation belonging to cluster B, which are closest among all such pairs. Now, that particular those particular observation and the distance between those particular observation is taken as the value. So, which is defined as minimum distance matrix. So, you can see the formula itself in the slide, capital D A B, minimum of D I J. So, all such D I J. So, D I J could be where I is ranging from 1 to m and j is ranging from 1 to n. So, I is for denoting for all the observations that belong to cluster A, and j is denoting all the observation from 1 to n which belong to cluster B. So, we are supposed to find that particular pair of observations which are closest, and then that distance between those two observations is taken as the distance between clusters. So, this is the first metric for computation of distance between cluster. The second one is the maximum distance, also called complete linkage. So, how this particular metric is defined? So, here we typically typically find out the observations, two observation, one belonging to cluster A and the another one belonging to cluster B, which are farthest from each other. So, among all among all pairs of observations, one belonging to cluster 1 and the another belonging to the other cluster, and among all such pair of observations we find out the observations which are farthest from each other, and the distance between these two observations is taken as the distance between clusters. So, the same idea is defined here in this slide, capital D A B, where we are taking maximum of D I J, where D I J is indicating the distance between observation I and j, where I can be 1 to m because it is referring to the cluster A, and j could be 1 to n because it is referring to cluster B. So, in this fashion, this second metric, maximum distance metric, defines the distance between two clusters. Let us move forward. So, our next metric is average distance or average linkage metric. So, here what we do is we take average of all possible distances between observations from one cluster to the other. So, observations from one cluster. So, one particular observation from cluster A and the other observation from cluster B, and we take the distance, and similarly we identify all such pairs between observations of cluster A and observation of cluster B. So, in a sense it will include all all the distances, all the observations connecting to all the observation connecting to all the of A, connecting to all the observation of cluster B. So, all those distances are computed and the average of those distances is then taken as the average distance. So, the same thing is defined here in the slide as well. To capital DAB, average of Dij. So, Dij is the distance between two observations, one belonging to cluster A and the other one belonging to cluster B, where I is referring to 1 to m and j is referring to 1 to n. So, here all possible distances between observations from cluster A to cluster B are then considered and the average is computed, and that average value is taken as the distance between two clusters. Now, this brings to our next metric, that is centroid distance. So, let us understand how this particular metric is defined. So, centroid distance is defined as the distance between two cluster centroids. Now, when we say centroid, we need to define this. So, how centroid is defined? So, centroid is the vector of coordinates values computed by averaging measurements of each variable for all the observations in the cluster. So, for each cluster, for each variable and for each of those clusters, we need to take average values within the cluster for that variable, and that value will become one of the coordinate, and similarly for other remaining variables will also compute these average values within the cluster for all the observation in a cluster, and that value those values will become part of the coordinate for the centroid. And once these centroid and the coordinates of these centroid for each of those clusters are known to us, then we can compute the distance between those two centroids. So, if we look at this, centroid of cluster A can be defined as below. So, you can see x a bar. So, we are referring to centroid A. So, you can see here the m coordinates that are there. So, first coordinate is being computed as the average value. So, because there are going to be because there are m observations in cluster A. So, we have multiplied by 1 by m, and then summation for all the observation x1 i's, where 1 is representing the variable 1, and xi where I is ranging from 1 to m, which is covering all the observations. So, we are taking the average of we are taking the average value for all the observation for a particular dimension, that is variable 1. Similarly, for variable 2 and up to variable p. So, because this is going to be a p dimensional vector. So, x a bar which is the centroid for cluster A, this is a p dimensional vector, and each of these p dimensions are being the value of for each of these coordinates belonging to each of those p dimensions are being computed by taking average value across all the observations. Similarly, we can compute for cluster B. Now, once the coordinates of centroid A and centroid B are known to us, we can define the distance between cluster A and cluster B as shown in the slide. So, capital DAB as equal to distance between x a bar and x b bar. So, x a bar and x b bar being the 2 points, and we can compute the distance between these two. So, this is how the centroid distance metric can be used to compute the distance between two clusters. Now, till now what we have understood, let us go through some exercise in R and understand a few of these concepts. So, let us go back to our R studio. So, we will have to repeat a few of the lines again. So, let us load the library. So, let us import this data set. Let us take the copy of this particular data set, and we are already familiar with the structure of this data set and the variables that are there. 17 variables in the original data set. So, if we are interested at looking at the observations, first 6 observation values we can see here, and then like we did for the previous lectures as well, we are going to change the scales, and then we are subsetting this subsetting a new data set for us, a new data frame. So, this is the remaining. So, in this one we have just the 15 variables. Then plotting for two variables, customer rating and price. This part we have already done in previous lectures. Normalization, this was also done. So, all this has been done. So, distance matrix. So, this part let us go through this part, distance matrix for first 5 serials. So, out of the 35 serials that we have in this particular data set, we can use this particular function dist function to compute the distances between these 5 serials. This is the function dist. If you are interested in finding more information about this function, you can always go into the help section and type dist. And then you will get more information about this particular function, what it does, and different arguments and the returned values. So, in the first argument, as you can see here, we are passing on the first 5 rows and just 2 columns of it, which are representing 2 variables that we are interested in. So, these variables are part of df1 which we need to compute before we move ahead. So, let us compute df1. So, in the df1, as you can see, we are considering just 2 variables. So, one is customer rating, the another one is price, and then we have also computed the normalized value of these 2 variables, rating and price. So, once this has been computed, normalized value have been computed. Now, you can see here in the dist function, the very first argument we are we have selected 4 and 5, which are actually representing the normalized values for rating and price. So, only these 2 variables are being considered in the distance matrix computation. So, the first 5 serials, the distance between these first 5 serials is being computed using normalized values of just 2 variables, that is rating and price. You can see the second argument, the method Euclidean. So, we are going to use Euclidean distance matrix here. The other arguments are for the presentation of the result. So, let us run this code. You can see in the output that the distance between the first 5 serials have been computed. So, this is in the matrix format. So, first serial distance of first serial from itself is going to be 0, then distance of second serial from the first one is this much, 1.52. So, these values we are able to see the values in this range because we are using normalized scale, right. So, in this fashion, this matrix is essentially giving us information about the distance between one serial to another serial. This is just for the 5 serials. If we are interested in changing the row and column names for these serials to indicate the name of the serials, we will have to use this particular code. So, we are going to run this. First create a matrix of this data, and then a few more transformation. For example, upper triangular part of it, part of this matrix we are making as NA, then we are changing the row names and column names, and then this is the matrix now. Now, because we have changed the name of columns and rows, so it will take more space for display. Now, you can see the names of cereals, high protein cereal, health card breakfast cereals, and similarly others. So, these are being shown as the row names, and similarly for column names. So, each cereal and its distance from some other cereal is being shown in this matrix, and how these distances have been computed considering the normalized values of just 2 variables, that is rating and price. Now, if you look at the values, these values are a number of decimal places have been used to accurately depict these values, distance values. If we are interested at looking at just the small matrix having just values up to 2 decimal point. We can run this part of code. Now you can see the values have been rounded off, and we can see the distances between different serials. Now, since we have done our discussion on the distance between two clusters, we talked about single linkage, complete linkage, and average linkage. Let's see how this can be implemented in R. So, if we if we take this example where we take the first two serials as cluster A, that means high protein serial and health card breakfast serial. If we consider them as part of cluster A, and the next three serials, that means special K multigrain and honey and Choco's chocolate and Choco's duet, these three serials we consider as part of cluster B, as you can see here in the commented part of the code. Then distance. So, now we have two cluster A and cluster B, and how distances between distance between these two clusters can be computed using different distance metric like single linkage, maximum linkage, and maximum distance, that is complete linkage, and the average linkage. So, let us see this. So, before we go ahead, let us look at the distance metric for all possible distances between observations from one cluster to other. So, right now we have just two cluster A and cluster B. Cluster A having first two serials, and cluster B having the next three serials. So, this particular code is will actually give us a matrix which is which would depict the distances between the observations from one cluster to the other. So, let us run this code. So, you can see here in the column names actually depict the cluster A serials, high protein serial and health carb breakfast serials, and the row names are actually depicting the cluster B serials, which is special K and then Choco's chocolate and Choco's duet. So, now we can also see the distances between the observations from the cluster B to cluster A and vice versa. Now, these are the distances distance values that we are interested in. The distance metric for cluster distance that we have discussed so far would actually require only these many values. So, single linkage, as we talked about, this is minimum distance. So, we need to identify in all these values which one is the lowest. So, which two observations are closest. So, we can just call this min function and we will get this value. So, let us run this. You can see 0.638157. If we try to identify serials associated with this minimum distance, then this is the distance, and we can see here Choco chocolate and high protein cereal. So, these are the two cereals which are closest to each other. So, the distance between cluster A and cluster B using single linkage can actually be will actually be this value 0.638157, and the observations which are closest are Choco chocolate from cluster B and high protein cereal from cluster A. Similarly, for the complete linkage distance metric, we can just use this max function, because we know that it is we need to identify the two observations which are farthest from each other. So, the max function will actually give us that value. So, let us run this code as well. So, we can see here the value comes out to be 2.48 this value, and if we find out this value in this matrix, then we will see that this is the value, and we see that this is the value, and the cereals associated with this distance values are Choco's duet and health card breakfast cereal. So, these are the two observations, Choco's duet belonging to cluster B and health card breakfast cereal belonging to cluster A, which are farthest from each other, and therefore, this value becomes the distance between these two clusters using the complete linkage distance metric. Similarly, we can compute the distance between two clusters using the average linkage matrix. So, we just need to compute the mean value for all the possible distances are already depicted in this particular matrix, and we just need to compute the mean. So let us run this part of the code. You can see 1.43. So here all the distances that we just saw in this particular matrix, so they have been, the average of these values have been taken, and that becomes the distance between these two clusters, cluster A and cluster V. So in this fashion, as we so we have been able to discuss the different distance matrix that could be used to compute the distance between two clusters, and we also did an exercise in R where we saw how this can be implemented in our environment. So we will stop here. Thank you.